Okay, so this is going to be me solving the practice final. So I've already gone through this on paper, there's more reliability in terms of not making any mistakes in this recording. And I don't plan on typesetting this. It's just gonna take too long, and I think it's unnecessary because I should be able to explain it just fine in video and in the handwritten export when I do that. Okay, so solutions. Right, let's begin. So obviously you should take stock of what formulas you're given. So you're given the projection formula, that's fine. You're given coordinates, change of coordinate formulas. You're given the second derivative test. These trig identities, which I think on one of the problems it was that I ended up needing to use it. I mean, or you could just rederive it, but it's given to you, so that's good. And then the formulas for line integrals. So, well, with these you should probably have done enough practice with line integrals and surface integrals so that you actually know these formulas. The tricky part is that you're not given Green's, Stokes, or divergence theorem. So those you have to remember, but okay. All right. So let's get started. So for number one, right. So this problem is a lot similar to a problem back in exam one, I believe it was. So it somewhat has to do with the geometric formulas behind dot product and cross product. So you have to remember that dot product is magnitude of things times the cosine, whereas the cross product is magnitude of things times the sine. So in particular for A, so A dot with E is equal to the magnitude of A times the magnitude of E times the cosine of the angle between the two. And so, and okay, so in this problem, we should kind of pay attention to the fact that all of the angles are multiples of 30 degrees, and all of the vectors have length 3. So that'll come into play with our calculations. So that the length 3 means that these two magnitudes are just equal to 9, and the cosine of theta. So A to E, 1, 2, 3, 4. You see, it's 4 multiples of 30 degrees. 30 degrees is pi over 6, so 4 times pi over 6, which is 2 pi over 3. And then if you think about the unit circle, 2 pi over 3 is on the negative side of things, so don't want to put it here or elsewhere. I'll put it here. So cosine and sine is like so. If you're talking about cosine of 2 pi over 3, you're on the negative side of cosine. 60 degree angle. Yes, a 60 degree angle means that cosine takes the value 1/2, so you get negative 1/2. So you get negative 9/2 for part A. For part B, the magnitude of this cross product. So we had a formula for that. So that is equal to the magnitude of B times the magnitude of F times the sine of the angle between the two. Again, the two lengths are both 3, and so it's going to be 9 times the angle between the two. Going from B to F, I think it's the same. 1, 2, 3, 4. Yeah, it's the same. So it'll be sine of the angle 2 pi over 3. Well, for sine, that's a positive value. 60 degree angle means it's a root 3 over 2. So we get a 9 root 3 over 2. Kind of want to box these two answers. And let's see, for C, again we have a dot product, C dot E. So again we use this dot product angle formula, C dot magnitude of E cosine of the angle between the two, 9 cosine, and this time it's 2 times pi over 6, so it's going to be pi over 3, 60-degree angle, so that's going to be a half, which gives you 9 over 2 for this. For D, okay, D has a bit more of a geometric way of thinking about it. So we're talking about the magnitude of this vector D minus G. So it would be nice to actually, I hope I didn't move anything. Okay, I'm moving something, that's not good. So D minus G, so notice that D is going this way, and then minus G is actually, it would be going this way, minus G. And so this overall vector, right, we add vectors tip to tail, or head to tail. So this is the vector D minus G, and we're looking for the magnitude of that. Now both of these sides are of length 3 by was given, and so this is a 45, 45, 90-degree triangle with sides 3, 3, and 3 root 2. So we can pretty much immediately conclude just from geometry that this the magnitude of this vector is 3 root 2. And let's do the last part. So A dot A. Hopefully remember that there's a formula for that. If you don't, you can still compute this just by, I guess, just by thinking about what the component form of this would be. So it's just whatever quantity in the I mean, if you write this as a vector, it would be 3, 0, right? If you oppose the usual coordinate system, and then you could dot it with itself and you get 9. But the way to do it without coordinates would actually be to know that A dot A, a vector dot itself, is equal to the magnitude of that vector and then squared, right? You can think about what these quantities mean. So like a vector dot itself, if you actually fully specify what that dot product is, it's you're squaring each of the components and then you're summing them together. Well, that's the same as squaring the magnitude, right? The magnitude of a vector is, you're using Pythagorean theorem, so it's going to be the square root of the square of each of the components summed together. Taking that square gets rid of the square root on the around all of that, and so you have this identity. This identity is what you're supposed to take away from this. And of course, well, magnitude of A is 3, so this is equal to 9. All right. So either way you do it, you have to show a little bit of work, I would say, just to make it clear how you're getting what you're getting. Don't just randomly write a number down, because then we have to think about, like, did you just randomly pluck a number from nowhere, or what? So try to give a little bit of justification. All right. Number two, Lagrange multipliers. So, yeah. So we're given a function, we're given a constraint. We want to find the maximum and minimum of this function subject to the constraint. Lagrange multipliers means that we're solving the system of equations gradient of f is equal to lambda gradient of g, where g in this problem is given by the constraint function. If you really want to spell it out, you can say g is the function x squared plus y squared plus 4z squared minus 36. Okay. All right. So yeah, maybe I'll just also fully specify this out. So it's solving this system, right? So the first equation here will actually give you 3 different equations, and the last guy's the 4th equation. Right, so let's compute the gradients here. So gradient is going to be, yeah. So it's going to be 2x, 0, 6z is equal to lambda 2x, 2y, and 8z. And of course you have g equals 0. So then that gives you the equations 2x is equal to 2 lambda x, 0 is equal to 2 lambda y, and 6z is equal to 8 lambda z, and g equals 0, which I will just copy down g again. So that is x squared plus y squared plus 4z squared is equal to 36. Right, so we have a system of 4 equations. Right, so we want to solve this system. What draws my attention is the second equation. Okay, so by looking at equation 2, it says that either lambda is 0 or y is equal to 0. All right, which one is easier? Lambda equals 0. So if lambda is equal to 0, well, then this first equation is going to say that x is 0, and the third equation is going to say that z equals 0. So equations 1 and 3 will imply that x is 0 and z is 0. And notice we don't have anything specified about y for this branch. Okay, so if we now look at the constraint, the constraint will reduce, because x is 0 and y is 0, it will reduce to y squared is equal to 36, which implies that y is equal to plus or minus 6, which gives us our points, 0, plus minus 6, and 0. Okay, so these are two of our constrained critical points. On the other hand, if we have that, if we take the other branch, and we take that y is equal to 0, well, that's not going to affect the system that much. This equation becomes 0 equals 0, which is not helpful. So system reduces to 2x is equal to 2 lambda x. Do I want to... So it's a question of, do I want to simplify out the numbers? For now, I'm just not going to do that, but you can see that we can cancel out 2's from both of these equations. 8 lambda z, and, well, if we set y to 0, then we have x squared plus 4z squared equals 36, making up our reduced system. So from that, I do want to move this, I think. So this is going to give us, let's subtract this over to the other side and factor things out. And so that will give us 2x 1 minus lambda is equal to 0. 2z 3 minus 4 lambda equals 0, and x squared plus 4z squared is equal to 36. Okay. Right. How much branching was there? I'm trying to revisit what I did before. Okay, so I think I can just do two subcases from equation 1. So equation 1, in this case, says that either x is equal to 0, or, I don't need that comma, x equals 0, or lambda is equal to 1. Okay. I'm trying to figure out if the way I've laid this workout is clean enough or not. Well, either way, let's continue this on here. So if, and I'm indenting it slightly, so if x is equal to 0, well, then the constraint becomes 4z squared is equal to 36, which then means that divided by 4, z squared is equal to 9, which gives you that z is equal to plus or minus 3. So that gives you the constrained critical points of, so in this branch we had 0, 0. So x was 0, y was 0, and we end up with plus or minus 3 for z. The other case is if lambda is equal to 1, right, then x is not specified. Lambda is equal to 1. I think it's going to do something to, yeah. So equation 2, that ends up saying that 6z is equal to 8z. So equation 2 becomes 6z equals 8z, which implies that z is equal to 0. So in this subcase, we end up getting that y and z are equal to 0, which means that the constraint has now given us that x squared is equal to 36, which means that, well, x is equal to plus or minus 6. Which gives us two more constrained critical points, plus minus 6, 0, and 0. So we found, in total, we found 6 different constrained critical points, and we need to evaluate our function on all of them. So, okay, I don't have enough space on the version of the page, so instead I have to actually evaluate off to the side. But we're going to plug in and, let's see, so our function f is like that. So that's really nice to plug into because the branches, the plus and minuses end up evaluating similarly. So I will just abbreviate that. So we had we have to do the following evaluations. What was the other one? Plus minus 3. Okay, 0, 0. Plus minus 3. So these are the 3 evaluations that we have to do because those were the constrained critical points that we had found. I'll just underline them. I don't think it's snapping, but that's fine. Oh well. Right, so those are the 3, and we're going to plug them into the function f given above. And so you can see that this ends up being 36, this ends up being 0, and this ends up being 3 times 3, 27. Yeah, 3 times 3 squared, 27. And so from that, you can get 0 is our minimum, and not 27. 36 is our maximum. Okay. I guess I will, I don't know, should I just box it like this? That's probably fine. We'll see how the export works. Okay. Yeah. For number 3, this is a volume integral over a Cartesian box, right? So this is, there was a funny mistake that I think I saw in like the 3rd exam. So the way that you read this, in case you don't know, like this is the x-coordinate, this is the y-coordinate, and this is the z-coordinate. So these are written in order. So that informs you on the bounds that you set up the integral. Okay. This triple integral is over this box. And so I wouldn't do anything with, like, I'm definitely not doing any coordinate transformations. So you just have to write it out. It's not terrible, but it's a little, there's a few steps to it. So we're talking about a triple integral z plus, I'd put parentheses there, x e to the xy. And Well, really any of the orders could be done. I'll just stick with, like, I don't know, the usual order, dx, dy, dz. So if I'm doing it in this integration order, then x goes from 0 to 1, y goes from 0 to 2, z goes from 0 to 3. So notice how things pair up, right? So the innermost pairs up, the middle one pairs up, and the outermost pairs up. Okay, that's how you write these things. Right, now, as part of evaluating, I would not do this as an iterated integral, because that to me just, that doesn't look as fast. I mean, in the first place, this is not the right order for iterated integral. You don't want to integrate this second term in terms of x first. You actually want to do it in terms of y first. But before all that, I would actually split this into a sum of two iterated integrals. Oh, and in fact, that should probably be my first step. Yeah, you know what? So since this is being recorded, I may as well just kind of erase things. Let me see if I can just save my time. Can I just copy that? I have to grab my keyboard. Okay. Yeah. Well, it's not. Kind of, partially. Partially. Okay. So what I'm saying is that this is a triple integral. Z on the outside is completely fine, but you actually don't want x and y in this order for this integrand. You want. Let me just move this back into place. Let's see. Oh, okay. You want these dy dx. Because if you take the y integral of this, undoing the chain rule is going to cancel this x on the outside, right? So the y integral should come first, and so it would be in this order. Okay. Yeah, so that's a little bit better. And well, let's first start with this this leftmost integral. So this is really quick because the dx and dy, you can strip those two integrals out, which will just contribute a 2. So 2 times 1, right? So you have 2 times the integral from 0 to 3 of z dz, plus all of that, which I will do in a second. This integral is going to be z squared over 2, evaluated from 0 to 3, which is going to be, the 2's cancel, you end up with z squared, so you get 8. Okay, for that part. Wait, no, something's wrong. Oh, I'm 9. You get 9, because it's 3 cubed. 3 squared. 3 squared. I don't know. I'm jumbling something. Okay. Right, so now for this one. Before I evaluate the inner guys, notice that the integrand is independent of z. So I can strip that z integral out, and it's going to contribute a 3. So really, we're going to be taking this integral, x e to the xy dy dx, and let's proceed to integrate this. So now, this one we do treat like an iterated integral, since we can't split this into 2 independent functions, one just of x, one just of y. I mean, no, well, technically we could, but it won't be useful. You could do it, but the x integral would be of the function x e to the x, and so I don't want to do that. It's easier just to take the y integral. Taking the y integral, that's going to absorb the x outside, and you end up with this. And now we would evaluate this from y equals 0 to 2. Notice how I'm specifying which variable I'm plugging in. That's just to make it very clear to myself, because otherwise I would sometimes confuse myself if I didn't. All right, now, Let's do the substitution. So y is equal to that. That's going to give me a 2x minus, and now e to the 0 is 1. So we have this as our next step. Okay. Just double checking. Yes. So finally integrating this guy, you get a e to the 2x divided by 2 minus x, evaluate from 0 to 1, and that's going to give you a, so plugging in 1, I get a e squared over 2 minus 1, and then if I plug in 0, so notice actually this is somewhat important because plugging in 0 just doesn't just give you 0 in this case. This exponential ends up giving you a 1/2. And so, if we clean this up a little bit, it's a little bit bothersome to do that. I mean, I think that if you wrote it like this, I would accept it. I would accept it at this point. But in terms of presenting, I would simplify this because there's a number here that you can cancel out. So minus 9 plus, you can see that you get a minus 3 over 2, so you get a minus 9 over 2 when you multiply by 3, plus 3e squared over 2, and then simplifying that fraction, 18 over 2 minus 9 over 2, you get 9 over 2, plus 3e squared over 2, I think is the same as what I got. Yes, it is. Okay. So I'll box this guy. Really, it should be able to just... Yeah, okay. I'll box that guy, but you could totally have left it in this format. That would have been fine also. Don't be too creative about that, because otherwise I'd have to, like, compute whether they're equivalent or not. Okay. Number 4a. So this is a scalar surface integral, or no, sorry, a scalar line integral, right? So the thing we're integrating, the function, is a scalar function, f. We're integrating it over a curve c, and it tells us it's a line. Okay. So the reason that that's important, right, because scalar line integrals, you always need to use the parameterization. So, I mean, in case you don't have it memorized, I'll write down the formula. I guess I'll write it off to the side. So, f d r, no, without a dot, it feels weird. I guess I'll just keep it like that. I'll do f ds, right? So this is a to b f of r of t dot with the magnitude of r prime of t dt, right? You have to insert your parameterization, and doing so, the parameterization r of t, and doing so will give you that formula, right? This is the formula that's on like the first or second page of this test, so you can copy it from there if you don't have these memorized. So first, to do this, we need the parameterization. We're told that the path is a line, and that's important. So we need to parameterize a line from these 2 points. I'm actually noticing one thing, which is, I believe, order should actually matter. Like, the way you parameterize this should matter. If you do it in the other direction, that should introduce a negative, if I'm not mistaken. But it's most sensible to say, like, you start at this first point and you end at this second point, right? It's probably not the case that you would swap these two by accident. Okay, well, regardless, let's write the parameterization. So I would like to say that that's clear. You start at 1, you go to 2, so it's going to be 1 plus t. You start at 3, you go to 5, it's going to be 3 plus 2t. So what I'm doing in setting up the parameterization is I want t to run from 0 to 1. And so I'm making it so that at 0, it starts at this point, and at t equals 1, I get to this point. So the coefficients in front of the t's will just be the how much change occurred. So 3 to 5, the change that occurred is 2. 0 to 4, which is the last guy, the change that occurred is 4. So, and we start at 0, so it will just be 4t. And so just to make it clear, I'm going to specify that this parameterization is from t going from 0 to 1. Okay. Right. What are we doing now? Next, we need to compute the derivative, right? Looking at this formula, we need to compute the derivative, and then we need to compute the magnitude. So the derivative is 1, 2, and 4. We're taking the derivative with respect to t. Now for the magnitude of r prime. So that's going to be the square root of 1 plus 4 plus 16, which is square root of 21. Right? Now that we have all of that, we can substitute into the formula. Well, okay, I'm not going to say a to b. I'm going to actually use the bounds for the parameterization. So 0 to 1, and then we plug into this f, this parameterization. So that says 3 times the x function, which is this first argument, first component, minus y times z. All right, now that's where it gets a bit messy. We have a 3 plus 2t times 4t. Let's put all of that in brackets. Oh boy. Okay, I'm going to need to move things off to the side a bit more. I guess I might put that. Should I put it all the way there? Maybe. Boom. Okay. So, because this was f of r of t, this part, we still need to put r prime, which is the square root of 21. And then dt. So that's what the formula says. And then we can go ahead and compute this integral, root 21. I'm going to pull that out right away. You can simplify the function inside. I'm going to refer to what I did before to fully simplify it out. So it's certainly a polynomial, and then we may as well... I won't write it in polynomial order because I apparently didn't do so before. So it's going to be 3 minus. So it ends up being 3t minus 12t, which should be 9t, minus 9t. And then minus 8t squared dt. So then integrating that, you would end up with 3t minus 9 over 2t squared minus 8 over 3t cubed, evaluated from 0 to 1. Doing the evaluation, well, okay, if you're given a calculator, it's not too bad. Otherwise, there's a bunch of fractions to work with. But you can see by plugging in 0 gives you 0, plugging in 1 gives you 3 minus 9 halves minus 8 thirds. And so the answer you'll get from this is square root of 21 times a negative 25 over 6. That is what I'd write as the answer. You can't simplify it. Well, okay, you can simplify it, but it doesn't help. So I would just leave it in that format. Yeah. I believe what I was saying was right, actually. So if you were to actually flip the parameterization, you could view that as either putting a negative here, or you could view that as flipping the time parameter t. So that will end up flipping this, the integral order, and so that should introduce a negative and get rid of the negative that shows up here. So this problem, I think, is not completely specified. Like, it should tell you the order exactly, but if there's ambiguity on our part, then we'll accept both answers. Okay. All right, for part B. Now this is a vector line integral. Piece of the graph y is equal to x squared between x is 0 and x is 3. So this is telling you, this is specifying the curve exactly. You can create a parameterization of the curve. But before we do that, we should think about whether we need to, do we need to evaluate? So the thing is that if your vector field is a gradient vector field, then by fundamental theorem of line integrals, you would know that instead of integrating over the curve, you could evaluate the potential function at the endpoints. But this function is not. So this vector field is not conservative. So this is a check that I would do if I remember to, which you should try to remember to. Usually, the thing that would telegraph that that it's a good idea to use FTLI is that the curve is hard to parameterize, or whatever integral that you set up would be hard to compute. In that instance, then that would kind of hint to me, maybe try something else. In particular, maybe there's one of those theorems, so FTLI could show up. But in this case, this vector field is not conservative, so we can't do that, right? How do we check that it's not conservative? Well, we check the cross partials property. If we take the y derivative of this, compare with the x derivative of this, well, the y derivative gives you 6, the x derivative gives you 0. They're not equal, so this vector field cannot be conservative. So since it's not conservative, we can't think about this in terms of evaluating a potential function. Instead, we have to do this through actually parameterizing the function, the curve, and computing the line integral directly. All right, so all that preamble over. Our parameterization, R of t. So this graph, it should be clear how we parameterize this. You let t be your x, and then, well, this tells you that the y is t squared. And these bounds tell us that t runs from 0 to 3. And since we're going to need it, we should compute the derivative of this vector function. So it's going to be 1 and 2t. We don't need the magnitude because we're doing a vector line integral, not a scalar line integral. So this vector line integral, the definition of how we compute this thing is that it ends up being f of r of t dot, this is a vector dot product, r prime of t dt. Okay. Inserting things in, so let's see, the f of r of t, I'm inserting r into f, so 6y ends up being 6t squared, and 2 is just 2. R prime, we computed already, so it's that, and dt. Okay, doing that dot product, we get a 6t squared plus 4t dt. And integrating, we get, let's see, t cubed over 3 plus a t squared over 2, so that there's cancellations because the numbers are nice. Evaluate from 0 to 3. At 0, it's 0. At 3, it's 27 times 2, 54, plus 9, 18, so that's going to be 72, I think. If I did my arithmetic correct. Looks like I did. Okay. So far, so good. Okay, now we have a vector line integral. Vector field looks a little bit messy. The function also looks a little bit messy. Or the domain, or like the curve itself. C, it looks a little bit messy. Right. Um, okay, so yeah, now I remember this. This one's a little bit. This one's interesting. It's a little bit difficult. So first, let's start by. How do I want to say this? Yeah, I. Oh, that was not good. Let's start by drawing a sketch of this. So this ellipse, right? The 9 in the denominator for x tells us that x goes from -3 to 3, and the 25 in the denominator for y tells us that y would normally go from -5 to 5 if we were... Okay, so unfortunately this is not going to trace out the ellipse. I'm not going to be able to draw a good ellipse from this, but we can pretend that it's an ellipse. Pretend that it's an ellipse. Okay. Well, and the note, the problem says it's the upper half, so we can. It might be better to actually ignore that bottom portion of the graph and instead just have this oriented clockwise, which is interesting that we're oriented in this way. How do I want to do this? Let me do that. So that is C. All right, so C is in blue. Now, let's see what happens if we were to think about if we were to try to do this directly. Okay. If we tried to do this directly, we would need a parameterization for the ellipse, which is not impossible. The way I would have thought about this is that I would start by orienting it the wrong way around. I would use the standard orientation, which would give me, which would give me x as the x function 3 cosine of t, and for the y function 5 sine of t, where t would run from... Okay, so I'm gonna kind of label it different. I'm gonna label it a little bit differently. So t would go from 0 to pi. I'm labeling it like this because we're going to want to flip this orientation. So there are two ways to then orient this correctly. So this is oriented counterclockwise right now. Right, you can see that if I plug in 0, I end up at this point at 3, 0. And if I plug in pi, I end up at this point, -3, 0. So this ends up being oriented the wrong way around. If we want to orient it clockwise, you can either flip these bounds, which makes sense in terms of integrals. It doesn't make sense in terms of thinking about intuitively how time runs. The other way you could flip it is you'd introduce a negative into the x function, because that will flip which side you are on. So I would then write like this. So you'd have -3 cosine of t, 5 sine of t, and again this is going to run from 0 to pi, but now this is oriented clockwise. I don't know if clockwise is really abbreviated like this, but yeah, whatever. So that would work, but now if we think about how this line integral would operate, right? This line integral, you would plug in the parameterization, so you'd do f of r of t dot with r prime of t. R prime of t is fine, but f of r of t would be crazy. It's possible, and you probably could expand it out and then actually take that integral, but the point is that looks overly complicated, at which point you should try thinking about, is there a simpler way to do this? And the answer is yes. this, but it may not be clear that's the case. Well, okay, maybe with this additional sentence here, state any theorems used. Maybe with that, it should give you a hint. Okay, you should be trying to use a theorem. Which theorem? Well, we're talking about a line integral. It's bounding something that looks flat, so you should be thinking of Green's theorem. Okay, so you should be thinking of Green's theorem. Now, to make it work, we need to introduce another curve, namely this curve, running from 3 to -3. Now that we have that, we will then have a domain, which I'm drawing in red. So I'm going to call that D, and I guess I'll call that C. What did I call it over here? I think, okay, so I just called it L because line. Okay, so Green's theorem, let's recall what Green's theorem says. Green's theorem, so it typically wants curves that are oriented clockwise, or not counterclockwise. So Green's theorem, it usually wants the boundary to be oriented counterclockwise, whereas here it's clockwise, which means that we will need to probably introduce a negative somewhere. Okay, but in general, what Green's theorem says is that if you're taking a circulation integral, right, a line integral over a closed curve, you can relate that to the double integral over the boundary, or no, over the full domain that the curve encloses, meaning that C should be the boundary of D. And then you end up doing it was qx minus py, qx minus py dA, right? Where f is the vector function p comma q. Right. So this relates for us line integrals along the boundary with area integrals along these two-dimensional regions. So, but what's tricky here is that the boundary of this shape is comprised of two parts, C and L. C is what the problem asks us for, but in order to do Green's theorem for this problem, we need L, and then we need to subtract L off, right? Because this double integral is going to give us the integral of C plus L. We then need to subtract off the integral of L to then solve for the integral of C. All right. In other words, integral of C union L, okay, f dot dr will be equal to the double integral along D qx minus py dA. Okay. And how hard is it to set that up? Well, all right, let's compute qx and py. So qx, just looking at this, so this guy ends up being p, and that guy ends up being q. That should be pretty clear. So qx is going to be 2y minus 4. Py is going to be 2y minus 4. Well, so that's rather nice, because these cancel it out completely. So that's perhaps overly nice. I mean, it kind of would be difficult to integrate over an ellipse. Okay, so maybe it's fair. Maybe it's fair to say that the integral should simplify that drastically. Otherwise, you'd have to you'd have to set up an integral over an ellipse, which is possible, but maybe bothersome. Okay, anyway, this turns into the double integral of the function 0, dA, which is simply 0. Okay, so that is a partial result, sort of stepping towards our answer. In order to isolate the line integral for C, we also need okay, yeah, so that is a nice thing here also, because it's 0, right? What I mentioned about orientation, it's not visible here. But if this was a non-zero value, say that this was 1, this 1 would actually correspond to both C and L being oriented in the other direction. So then when you sort of combine everything together at the end, instead of the value 1, you'd have to use -1. So orientation is something you need to pay attention to, right? Green's theorem, the equality for Green's theorem works if your boundary is oriented in the right direction, namely counterclockwise. But here, because this value is 0, -0 is just 0, so it works out nicely. All right, the next thing we need to compute is this line integral. This integral over L. Okay. Well, so it's a vector line integral, and we may as well compute we should probably set up a parameterization. So I'm going to do so. We could do it like this. Well, I mean, I think we should do it like this because t goes from 3 to -3 is maybe how I would write it, right? So we have to start at this point, and we have to go end at this point. So we start at 3, we go to -3, and it's a line matching up with the x-axis. So that is our parameterization. Clearly, our prime of L is going to be 1, 0. So when we plug in our parameterization, we go from 3 to -3 like that. And then f of r of t, what is f? F is this function. If we plug in that, so the y's go to 0. So the first argument is just, wait, do I need to spell it out more? Okay, to be safe in terms of, yeah. So I will spell it out. I'll give it one more step. So f of r of t dot with r prime sub L of t dt. And now we go ahead and compute this guy. So plugging r into f, first guy's 5, second guy, so x becomes t and y becomes 0. So this term goes to 0. This becomes a -4t plus 9, which I think ends up not mattering anyway because we're dotting it with, we're dotting with 1, 0 dt. So it doesn't matter except to show your work completely. So 3 to -3. Whether you decide to flip the, I probably would flip the, I would probably flip the integral at this point. Let me do that. Let me flip the integral. So flip it into just a negative. Taking the dot product gives you 5 dt. And so that's a really easy integral to compute. You get -5 times the length of the line of the integral, which is 6, so you just end up with a -30. Okay. Now, take stock of what we've done. We computed, by Green's theorem, the integral along D. We computed the line integral L. So, from that we can compute the line integral c. Right. The point is that, how should I do this? The point is that the line integral along C will be equal to the line integral along C union L minus the integral along L. And so this guy ends up being 0 minus, and then it's a negative 30. Therefore, you get that the line integral over C is equal to 30. So that is the answer that you should get at the very end. And yeah, it's bothersome to spell out orientation here, but you can barely see that's happening here. So I guess the right place that you would have introduced a negative, this is all a very technical consideration, but it may play a role if the problem is not set up so nicely. But really, there needs to be a negative. I'd say, should I say here or here? I'd say here, because both of these are positive. So when you think about this double integral, that's fine. But by Green's theorem, that's related to the integral along the boundary of D oriented in the counterclockwise fashion. So it would be oriented this way, opposing both of these. Which the way to kind of express that would be that if we were to follow the integral along the orientations C and L, we'd have to introduce a negative. But because we're talking about negative 0, that's just 0. So that doesn't show up. But yeah, it would. But if this was non-zero, that would affect the value here, which would affect the value here. That would affect the final kind of comparison that we would do. Okay, but yeah, in this case, we get 30. I hope that was clear. Okay. Next problem, number 6. So let's see. When I look at this, the first thing I see is that this is R. R is less than or equal to Z is less than or equal to 3. This value is definitely bounded below by 0. If I start thinking about the cross-section that we could depict this in terms of, so this would be R and Z. This would set up the, well, okay, so Z is at most 3, and that kind of means R is at most 3, because we actually have that, we actually have this line. This line is Z is equal to R, which is, yeah, when those are equal. So you can now imagine that this region E is this cross-section revolved around the z-axis, and revolved, well, okay, so not fully revolved. This x greater than 0 means that we're talking about these two quadrants, which you could label it as saying that theta goes from minus pi over 2 to pi over 2. Okay, so it's not the full circle, but it's half of the circle. So these two pictures combined together, they indicate that you should be using cylindrical, right? And, well, it definitely use a three-dimensional coordinate system, so not polar. Could you use Cartesian? Maybe, but the domain in the xy plane is a circle, a semicircle, so it's a little bit bothersome in Cartesian. Spherical it would be hard to capture this flat top and spherical. So cylindrical makes sense. I would say cylindrical because it's a flat top. Cone, well, cone with flat top, maybe. Cone with flat top. Cone with flat top. Right, if it had a spherical top, then I would use spherical coordinates. Right. Okay. And now let's just specify the bounds, right? Because that's the other part that this is asking for. So the bounds, why I said that theta goes from minus pi over 2 to pi over 2 by reasoning about this picture here. We also have, let's see, now we need to parameterize this. So I can see from that R could run from 0 to 3, and then Z would run from, you can see that the topmost guy is 3, and the bottom is going to be given by this line here. So that's just the line R. Z equals R. Right. You can think about it in the way that for any specific value R, maybe I'll use a different color just to specify. For any specific value R, the Z needs to range from this point to that point. The top point is constantly the value 3. The bottom point changes, and it's a function of R. Right? And so you end up with that for the bounds. So I would say that this works as expressing the bounds of the region E. You could write the whole set in terms of this. I feel like that's actually not necessary, so I'm okay with writing it like that. All right, now to do this integral. Okay, so we want to express this in polar, or no, in Cartesian. So yeah, sorry, in cylindrical, since this is written in cylindrical. I'm not gonna do that. Use a different color. So we want to do this in cylindrical. In cylindrical, x becomes r cosine of theta. Also, we shouldn't forget our Jacobian, so r. And then the fact that z depends on r does force, it forces a little bit in terms of the integration order. It forces that the z integral needs to be inside of the r integral. I suppose you could have also parameterized this triangle the other way around. You could go like z from 0 to 3 and r going from 0 to z. That's another way you could parameterize it, in which case you'd get like the other integration orders. Here, yeah, this cuts down the possible integration orders in half. So I think the easiest one for me to see is dz dr d theta. Right, z needs to be inside of r in order for this to work. So the z integral is inside of r, and then matching up the bounds, we would get minus pi over 2 to pi over 2. Okay, so this abstractly defined integral, right? This integral that's just defined over, or that's integrating over all of e, can be spelled out in this way. All right, integrate theta from minus pi over 2 to pi over 2. Integrate r from 0 to 3. Integrate z from r to 3. Okay. And now we go ahead and compute this guy. So the first thing I would do is, let's see, z, I'd really like to be able to split this apart, but I think can I split it apart? I think theta and r I can split apart. This function cosine, it doesn't depend on these first two integrals, so we can pull this out of these two integrals, and we can pull the theta integral out completely. What we're not able to do is separate z and r, because they are coupled. The z integral depends on r. So the most that we can do in terms of separating things is this. This is as far separate as we can make it. Now let's go ahead and compute this. So sine of theta running from minus pi over 2 to pi over 2 times, this guy I need to treat as an iterated integral, 0 to 3. So you'd get an r cubed over 3. I can pull the 1/3 out. Wait, no, sorry, that's not right. Well, you integrate this with respect to z. That's just going to pop a z there, and then you'll evaluate z from r to 3. So that is just going to give you an extra factor of 3 minus r dr. Okay, that looks right now. Plugging into sine, you get 1 minus -1. So altogether that would be 2. And then this one, r cubed over 3 when you integrate, and then this is r cubed, so then r to the 4th over 4 when you integrate, evaluated from 0 to 3. Let me just bracket that. 2 times, plugging in 0 gives you 0, plugging in 3 gives you 27 minus 81 over 4. I think that's right so far. Yes. And then doing that calculation will finally give you 27 over 2. Okay. Right. Yeah, so that's not too bad, I think. Main thing is make sure you don't forget the Jacobian. I think it's fair. All right. Number 7. Number 7. So we're computing this line integral. Let me just double check. Did I actually, in the previous thing, I did specify Green's theorem. Yeah, okay, that's fine. Good. So this one is also Green's theorem. But this one is a little bit nicer for you because it tells you that C, the boundary, includes the x-axis. So that is convenient. Although, I guess you could also kind of conclude that by knowing that this integral is over a closed path. Right. So let's picture what this region is. So we're talking about the upper half of a unit circle. So something like that is the path, oriented counterclockwise. So you'll have this part and this part. So if you were to compute the line integral directly, you'd actually need to sum two path integrals. You'd have to sum the line integral along the circular boundary, and you'd add that with the line integral along this line segment. By Green's theorem, and notice that the orientation is correct. Okay, so then by Green's theorem, we can instead express this as the integral along the along the inside. So by Green's theorem, f dot dr. Right, we can view this as f dot dr. Right, the dr is this vector dx comma dy, and f is this function and this function. This is going to be equal to the double integral along the boundary, along the domain d q sub x minus p sub y dA. We let this guy be q, that p, that guy be q, and so we end up with that. I'm gonna leave the integration specified in abstract. Let's compute the qx minus py. So qx is minus 2y, py is minus 6 dA. Okay. Right. So, because this is integrating over a half circle, you could re-express this. You could re-express this integral in polar. It actually, I think it ends up using a little bit more work to do it in polar, but it is doable, and maybe it's worth kind of doing that as like an alternative option. Well, first let's see what happens if we do this in. Oh, God. Let's do this in Cartesian. So in Cartesian, first let's pull out a -2. This is going to be y minus y plus 3. If I integrate this, so that's 1 and that's -1, and that's 1 up here. If we integrate this dy dx, that would be the order I would pick. X goes from -1 to 1. Y goes from 0. I need a bit more space. Goes from 0 to the upper half of a circle. So it's that function. We're half of a unit circle. Okay. Computing the y integral. Let's see. This would give you y squared over 2, and then you'd plug it back in. Y squared is going to square away that square root. So you end up with that. Evaluating at 0 gives you 0. If we integrate the 3, we will just end up with a 3 times the radical. So we end up with that. And so that is the inner integral done. Let's see. Something doesn't look right. One sec. I think there's something wrong with the 2 somewhere. There's a 2 somewhere that's missing. Oh, okay, I see what I did. Okay, now I get it. That is, isn't it? This is an even function. That part is even. I guess both of them. Both parts are even, but I didn't use that the other part is even. I actually split this integral into 2 halves. So because this part is even, that will introduce a factor of 2 when I cut the integral in half. So you can integrate over 1 minus x squared dx, and then you can plus this with a -6, minus 1 to 1 square root of 1 minus x squared dx. Alright, so what I did here is I split this integral between both of these terms. The -2 combines over. I factored out that 3, giving you this -6 here. But then I also used the evenness of this to of this function to say that instead of integrating from -1 to 1, we can integrate from 0 to 1 and then just double that. And so we end up with this. Integrating this gives me x minus x cubed over 3 evaluated from 0 to 1 minus 6 times. And then what's convenient about this integral is this is a geometric integral, right? This is, if we think about what the area is that this integral is computing, it's the area of half of a circle of radius 1. So this is 1/2 pi times 1 squared. Okay. Computing this, so plugging in 0 gives you 0, plugging in 1 gives you 1 minus 1/3, so that gives you 2/3, which in total gives you minus 4/3 there. This gives you a minus 3 pi. And so that is the answer for this. Do I want to do this in polar? It's not terribly bad. Maybe I'll try to rush through it a little bit. So alternatively, if you wanted to re-express this in polar, well, I think pulling out that -2 is still the same. And then you're still gonna be integrating y plus 3. Okay, maybe I'll just duplicate that. So y plus 3 dA. But if you use polar, this will become r sine theta plus 3. Don't forget the Jacobian, and then you'd have dr d theta, for instance. Yeah, either order works because this region is a polar rectangle. Theta runs from 0 to pi. R runs from 0 to 1. But in order to integrate this, so you can't split this like into a product of two integrals. You have to distribute the r across and then integrate both terms separately. I'm not going to go into detail on that. It's not that bad. You can do it. I did do it on paper, but I think it doesn't really teach too much to do it. Once there's a few steps that are missing. More than a few. But you'll still get the same quantity. You'll still get the correct answer. So after you distribute, then the first term you could then write it as a product of two integrals. And then this is the second term, since that's just 3r, you can pull out the theta integral. So it's doable, but at the very least, it takes the same amount of work. So it doesn't make it any simpler. Okay. All right. Number 8. Right. So this problem somewhat computationally heavy. So first of all, what is the region that this is describing? X, Y, Z. So X is supposed to be negative, which means that we're actually in the back here. Y is positive. We're talking about a sphere of radius 1, so let's maybe start doing some tick marks. And Z is negative. So really, these are the marks that we have. And maybe like that. So it's the portion of the sphere that is in the back right bottom octant. Okay, so this is 1/8 of a sphere of radius 1. And S is a surface. We're talking about the surface integral. So don't confuse this with the ball, where you actually have where it's a solid. This is only the surface, which means it's only this spherical part of it. Right. So you can guess that we're going to use spherical coordinates. And notice that this is a scalar surface integral. So we don't have any theorems to help us with this. We have to compute the scalar surface integral using the parameterization. First, maybe we can start with some of the setup things. So rho is equal to 1, since we're told that the sphere is of radius 1. Theta, let's think about theta. So if we think about it in the xy plane, we've said that x is negative, y is positive, which gives us this quadrant, which tells us that theta runs from pi over 2 to pi. And then phi, thinking about the three-dimensional picture, well, phi is going to start off over here at pi over 2, and it's going to go down all the way to pi. Right, so all the way to pi is the negative z-axis. Right, so once we set up our integral in spherical, we'll be integrating over that. I should probably recall how scalar surface integrals work. Right, so this formula is in the front of the formula sheet, but I don't feel like scrolling up, so I'm just going to write it down. Dot, no, not dot, normal. Take the magnitude of r, a function of u and v, and this integral is probably over du dv. You could also say dA if you are trying to be abstract about it. But that is how you compute a scalar surface integral. Once you've, there should be a prime here. Once you've introduced the parameterization, r prime. Okay. So our parameterization is going to be the spherical parameterization. And, well, it's kind of questionable whether you want to use u and v or you want to use phi and theta. You could certainly use phi and theta, but I'm going to opt to use u and v because that's what I did on paper, and it'll be easier for me to compare. So, u and v, in my case. So you would just copy the way that the coordinate, the change of coordinate formulas work for spherical. So you can grab those from the front page of the test. So the spherical coordinates, it would say rho cosine theta sine phi, but since rho is 1 in our case, we only need and I guess I'm just gonna I'll just mention that I'm using u for this, and I'm gonna use v for this, so that's just to help you compare, I guess, if you set it up a different way. So cosine u sine v, sine u sine v, and cosine v. All right. We take the conversion formulas for spherical and we set rho equal to 0, or no, equal to 1, and then replacing u and phi by u and v respectively, you end up with this. Theta and phi, I should say. Okay, yeah, so that is the parameterization we'll use, and then we need to compute whoops, wait a second. Yeah, no, this is not right. Okay. This is more complicated than that. How did I do this? What did the formula sheet say? T's or U's? T's or R's? T's. So it uses T's. I did not use T's. Well, it means the same thing. So fine, whatever. Tu cross Tv, and then take the magnitude. The point is that is the normal vector, right, on the surface. You take the two tangent vectors, you take their cross product. That result is the normal vector at the surface. So we end up needing to compute that. So tu, which is the same as the derivative of r in the u direction, the partial derivative, right? So that's going to be a little messy. Sine u, sine v, cosine u, sine v, 0. And then tv is the same as rv, is going to equal cosine u, cosine v, sine u, cosine v, minus sine v, like that. And, well, we have to take the cross product, which is kind of an involved calculation, but let's see. So we imagine there's ijk's there. So the first component is going to be this times these two minus these two. These two, I hope my cursor is visible in the recording. These two is minus sine squared v cosine u. And then for the j component, those two minus those two, but with a negative. So the negative is going to show up. You end up with a sine squared v sine u minus 0. And then for the k component, you get these two times these two. And something simplifies. Well, I'll just write it in full. So sine minus sine squared u sine v cosine v minus cosine squared u sine v cosine v. And so you can see that, well, all right, so, okay, thankfully I can copy paste, can't I? Okay, copy, paste. You can see that this last component, you can factor out the negative sine v cosine v, and you're left with sine squared u plus cosine squared u, which is simply 1. That means this ends up simplifying to just that. Okay. Yeah. Okay. And now we take the magnitude, because we'll be needing that. Tu cross Tv. So we, what do? We square, we take the square root of the square of each of these things, so that'll give me a sine to the 4th v cosine squared u plus sine to the 4th v sine squared u plus sine squared v cosine squared v. All of this is in a square root. That simplifies. So the first two terms, notice that if we factor out the sine to the 4th, we end up with a cosine squared u plus sine squared u, which is simply 1. So that becomes sine to the 4th v plus the other term. And now if I factor a sine squared v out of both of these terms, then we end up with sine squared v plus cosine squared v, which is 1. And so that simplifies to sine squared v in a square root. And then, well, the last simplification is to just simplify the square root of a square. Although one comment needs to be made about this. So I'll do it in a different color. So v is inside of the domain, well, pi over 2 to pi. And if you think about what the sine function looks like, it looks like that, where this is pi. So the important part is that sine of v is positive, which is what allows you to simplify this square root of a square. Whenever you simplify that expression, you technically need to be a little careful, because what if the thing you're squaring is negative? Then this simplification technically should be absolute value of the inner argument. So without knowing that the quantity, the sine of v, without knowing that that's positive, this would technically have to be the absolute value of sine of v. But because we can see that the domain that we're considering is where sine of v is positive, the square root of a square simplifies to just the positive branch of the absolute value function. Okay, so we have, I believe, the setup of everything that we need for parametrizing the integral. All right, now this is unfortunate because I'm kind of low on space. I guess I'll go off to the side from here. That's a... All right, come on. Scroll to the side. All right, so this double integral s x z d s, we're going to write this using the parameterization. So we want to plug r of u comma v into this function. So that's going to give me... Okay, so I'm going to take the product of x, the x function, and the z function. So it'll be cosine of u, sine of v, cosine of v, that's f, of r of u and v, dot multiply with the magnitude of the cross product of tangent vectors, which gives you a sine of v. Do I really want to write sine of v? I can do it. That's fine. That's fine. Just to... It's nice in your work if you kind of make sure that it's easy to double check that you did it right. All right, so now this is in terms of u and v. Let's set up our bounds. So both of these are from minus pi over 2 to pi. Oh, no, from pi over 2 to pi, I think. Yes, so those are the bounds. Okay, and... Well, this is really symmetrical, isn't it? Not, well, kind of symmetrical. I can split this into a function just involving u and a function just involving v. And so we have that. What's a good color? And so this is going to be sine of u evaluated from pi over 2 to pi times this. I would think of this as a u sub, right? You let u be sine of v, so then this ends up being the integral of u squared du. Okay, it's unfortunate I already have a u in this problem, but you know what I mean. This is a u sub type problem. The cosine v is part of the differential, the du. So doing u sub mentally, you'd get 1/3 sine cubed v. Plug it, evaluated from pi over 2 to pi. How hard are these evaluations? They shouldn't be too bad. So at pi, sine is 0, And at pi over 2, sine is 1. So it's 0 minus 1 times 1/3. I'll pull the 1/3 out of the evaluation. And so then it's, again, it's 0 minus 1. Cubing those quantities doesn't do anything to them. And so you end up with 1/3, which, yes, matches what I got beforehand. So there we go. That is the answer for number 8 in full. You're able to write smaller if you actually print the page out. So I was able to fit it in one page on paper, but somehow it's a bit more unwieldy to do it. Yeah. Okay. Number 9. Let's see. This is a vector field. We're taking the curl. S is the part of the sphere that lies in the cylinder and above the xy plane, stating the theorems used. All right. First, let's try to visualize what's going on. You could actually try to draw this in 3 dimensions. It's not terrible, but really the only thing you actually need to see is the profile in the RZ plane. So if we look at this in terms of R and Z, right, the sphere ends up being a circle of radius 3. And then saying that the cylinder is this, x squared plus y squared equals 1, that is going to be that. So what happens is we want the part of the sphere that lies in the cylinder. So that's actually just going to be this portion of the sphere that I'm coloring in blue. And then you can revolve that around the z-axis. Okay. So this is a spherical cap, basically, for our surface. Our surface, S, is a spherical cap. In 3-dimensional space. We could probably try to... It might be possible to actually integrate it directly. The curl of F is... I think it does simplify the vector field quite a bit. And then if you were to try integrating it, well, you'd have to do a very similar thing to what we have just done with parametrizing. Yeah, you would have to parameterize if you were doing it directly. Now, the point is that you probably shouldn't do it directly. Notice, right? So because of the structure of this integral, this double integral of a curl vector field, you should be thinking about the fact that this is related to such an integral, such a line integral by Stokes. Right? So instead of integrating along the surface, we could integrate along the boundary of S, which is just going to be a circle. Okay. It'll be a circle that is traced out by this point in red. So if you revolve that around the z-axis, that red point is going to trace out a circle. Let's now try to parameterize what that traces out. So before that, I need to do a small calculation. Because that point has x squared plus y squared equals 1. So I'm going to need to plug that into here. So that will give me that 1 plus z squared is equal to 9, which implies... is this how I want to write it, express it? Kind of. Yeah, that's fine. Yeah, so z is equal to... plus or minus, so it would be square root of 8, which you can pull out the 4, and you end up with 2 root 2. And we're only going to want the positive version because we're talking about the part of the sphere above the xy plane. Okay, so it tells us which z to use. Otherwise, I guess technically, if we were chopping the part of the sphere by the cylinder, you'd have an upper part and a lower part. All right. Okay, so we have that. The x and y coordinates of this circle that is traced out, you can think about projecting this down to the xy plane. So it will, when projected down, it's actually a unit circle. So the circle is just going to be cosine of t, sine of t, right? Radius is 1. And then for the height, the z height, it's what we just computed here, so it's 2 root 2. And I should say a bit more about the bounds of the parameterization. So t runs from 0 to 2 pi. Okay. Yeah. Right, so let's now compute that line integral. So just spelling out the definition of what it means to compute a line integral, given a parameterization. Right, so next we have something a little bit annoying. Is it annoying? It's annoying, but not too annoying. We plug the r into f. And so doing that gives me 2 root 2 cosine of t for my first argument. Y times z gives me 2 root 2 sine of t for my second. X times z, yeah. So that's where this is kind of funny, the way that this is structured. It's a bit, I wouldn't have anticipated this is the same function. Because I would be thinking of cyclical symmetry, but we don't have that here. Okay, so minus sine of t, cosine of t, and 0 when we take the derivative of r. So I didn't bother to write that ahead of time, but you could have if you wanted to. But that's r prime. When we take that dot product, you'll notice that you end up getting cancellation. Let me just say it's equal to 0. I don't feel like writing it out. So you can see the minus sine of t, cosine of t, and the 2 root 2. Right, you get exactly the same thing from coming from the y component, and then the z component is just 0. So the dot product is just 0, which means that this integral is 0. Okay, and so that is actually the answer for this problem. Right, so Stokes' theorem related this surface integral with this line integral, and we were able to compute the line integral and got the value 0. I'm kind of thinking about, I think technically with this problem, something should be mentioned about the orientation of the surface. We kind of assumed a outward pointing normal vector for the surface integral, which would then induce the counterclockwise orientation along the boundary. But yeah, that's kind of an assumption. I mean, I would say it's a safe assumption to make, but yeah, to fully specify out this problem, it should tell you something about orientation. Okay. But yeah, that's the right answer. Let's keep going. For number 10, determine if the vector field is conservative or not. Find the potential function if it is. Right. This guy... Okay, so well, maybe let's talk about the overall process of how this works, right? So for easy problems, usually what happens is you're able to like spot the potential function just by staring at it. In which case, if you are able to get that, then you can conclude it's conservative. But if you have a problem where you can't just stare at it and know, then the way to test things is to use the cross partial property, right? Compute all the cross partials and check that they're equal, which is equivalent to saying compute the curl of the vector field and check that that curl is the zero vector. If you have either of these, that curl of the vector field is zero or that the cross partial properties are satisfied, assuming as well that the vector field is on a simply connected domain, that implies that your vector field is conservative. It's kind of a long-winded sentence. But yeah, that is a way to prove or argue abstractly that your vector field is conservative. But in my opinion, it is always a far more concrete thing to just produce the potential function. At the very least, this check will allow you to quickly determine like whether you have any hope of finding a potential function at all. And if the check works out, then that can give you perhaps a reason to try doing this whole like integration matching up thing, because what you're trying to do with finding a potential function is you're trying to undo the taking of the gradient, right? So that means that you integrate the arguments and you try to match things up. Okay, I think that's enough of that recap of how this works. Let's work through things. So for A, how do I want to write this? So I'm going to call this guy P, this guy Q, this guy R. So we can, if I first stare at this a little bit, I don't immediately spot a potential function. So instead, I would try to compute some of the mixed partials. So for example, these two mixed partials should be equal to each other if the vector field is conservative. So if we compute that, we get 4xyz squared. Okay. If we compute... Wait. Sorry, that's the wrong way around. That's qx py. I did not mix them. Qx, so 2y squared z squared, and py is, the 3 is going to cancel, so you get 2y squared z squared. So that looks fine. Okay. But there's actually two more sets that you should do, and there is one that won't work. Maybe the other one doesn't work also, but the next one that I tried was Rx versus PZ. Right. By selecting these, it's the x function and the z function, so then we mix the partials. And when we do that, we get a 2xy squared z squared for r sub x. For the p sub z, we get a 4/3 y cubed z. And so you can clearly see Rx is not equal to PZ, which means that, I guess I should maybe say this as a bit more of a sentence, F is not conservative. Yeah. Okay. Right. For the next one, right. Well, so to be honest, this one I was able to do by inspection, but perhaps it's better to pretend that we start by doing the mixed partials. So p sub y and q sub x. So p sub y is minus 4xy plus 1 over 2 root x. And when we do q sub x, we get a minus 4xy plus, and then the square root function is just 1 over 2 root x. Right. So that is us checking the mixed partials. So far, so good. You could think that there is kind of an issue about the definedness of this part here. This kind of would make you think that maybe the vector field is not defined when x is 0, which I think ends up being fine because that just means you have two halves that the vector field is defined over, and over each half it is simply connected. So you could argue that it should be conservative from this, but the better way to really argue is that it has a potential function. But I guess for now I'll just box that. So conservative, sure. Potential function. So assuming that you can't just stare at this and see it, what you'd have to do is integrate p and q. You integrate p with respect to x, you integrate q with respect to y. Because remember, we're trying to undo taking the gradient. So, so on the one hand, we would be integrating p dx, which is going to give you a 2x cubed minus x squared y squared. Okay, integrating that is a little bit bothersome. Let's see. I would rewrite that as a x to the negative 1/2 power, right? So you'd be x to the negative 1. So you'd get the y over 2, and you'd just move that off to the side. You'd integrate this dy, which would end up giving you x to the 1/2 power multiplied by 2, so you'd end up with that, which you could then rewrite it as a y root x. Okay, and then you plus a constant, but the constant in this case you have to be careful about. F is supposed to be a function of x and y. This constant of integration is going to be a function of y. Let's call it c of y. Okay, because when we take the x derivative of this whole term dies, so this whole term looks like a constant. We also have, if we integrate q dy, this will give you minus x squared y squared plus 4y plus, and then this last term, when we integrate that, we just get a y root x. And the constant of integration here is, let me call it c tilde. I don't want to use prime because this is calculus. Primes look like derivatives, so I'll call it c tilde of x. So it's a constant function of x. Well, what am I saying? It's a function of x which looks like a constant with respect to differentiation by y. Okay. Right, and so both things need to be satisfied. So then we match up the terms in order to construct f itself. So from this we can gather that x does it ask for all? It says find a potential function. So this would be valid. If I wanted to go and just be like, here's every single possible potential function, I'd do a plus c. You don't need to put that plus c. But yeah, any potential function for this. Why did it not? Uh-oh. Yeah, any potential for this potential function for this vector field would look like this. Okay. Yeah. Very good. Right. Let's see. 11a. Suppose we know the gradient is 0. First, these second derivatives are positive. Do we need to know any more to determine if this point is a local min? Okay. So this is a conceptual question. A local min. So this is thinking back to the second derivative test and the whole usage of the discriminant, right? So for local min, what you should know is that the second derivative test says that d of 1, 1 needs to be positive, and also fxx or fyy, but we can use fxx is greater than 0. That is what we could use to conclude that 1, 1 is a local minimum, right, using the second derivative test. So we are told this part. That is fine. We are given that it's positive, but we don't have anything about the discriminant, right? Recall that the discriminant is fxx times fyy minus, I should make that look like a minus, fxy squared. We don't have that expression showing up, and we can't conclude anything about this from the data that's given. So what we should say is that we need that the discriminant evaluated at 1, 1 is greater than 0. So that is what I would put. Okay. Suppose that the gradient at 0 is 0, the discriminant at 0 is 0. What does the second derivative test tell us about how G behaves? So it's mainly to do with the discriminant being 0. So you can look back on, I think it's the second page on this test. So part of the cheat sheet or formula sheet, whatever you call it, it gives you the breakdown of the different cases, the 4 different cases for the second derivative test. And that last case says that if d equals 0 implies second derivative test is inconclusive. And yeah, really that's all you need to write. You just need to write that it's inconclusive. Maybe you could say specifically it's because discriminant equals 0. All right. Part C. What is wrong with this integral setup? All right, so this is a lot like, I don't remember if it was test 2 or test 3, but it's very similar to a sample problem, practice problem from there. I don't even remember if it was on the actual test 2 or test 3. It was on the practice. But yeah, so the problem, notice that the z integral depends on y, which is fine. That is okay. The main problem is that the y integral depends on z, which is kind of like it's reaching into the integral. So you can either argue that like the cyclic dependency thing, so cyclic not allowed. That's one way to argue this. The other way is to say that the bounds for your integral can't be reaching inside of the integral. They have to be reaching outside of the integral. So like, yeah, this is like reaching inside. Which is bad. So I guess I'll just say bad. Or otherwise you would write something about like the, oh. Yeah. One or the other, right? Okay. D. So, D. I think probably the actual. So this one I like. You're probably going to be asked to compute a Jacobian that is reasonable to compute. This is not reasonable to compute. So because if I remember correctly, this Jacobian I had computed in my notes, but because this is the Jacobian for converting between spherical and Cartesian, and that calculation takes an entire page, and the determinant that you're computing is a mess, right? So if I remember, that should be in the last section. I don't know if it was like 4.8 or 5.8, but it was the section on change of variables. Change of variables 5.7. Change of variables. So like near the end, I computed all those Jacobians from scratch. So you're not. So yeah, for this specific problem here, I'm not writing that Jacobian. I'm not computing that Jacobian. No way. No way. Although I will say, like, if you were to, if you were given a transformation that had 3 variables, and it wasn't like super crazy, you could do it. So, what you would do, you'd be taking these partial derivatives, right? You'd be doing y sub rho, y sub theta, y sub phi, and z sub rho, z sub theta, z sub phi. Right, you take these nine partial derivatives, you stick them in a matrix, you take the determinant of that matrix, and then that would be your answer. But because this is a well-known transformation, we can rely on our knowledge about the spherical coordinates, and we know that the Jacobian is rho squared sine phi, so there we go. I mean, it does just say find. It doesn't really say how to find. That's one of those jokes, I suppose. Okay. But yeah, actually doing this calculation by scratch, it takes a whole page. So yeah, have fun with that. Or look at the type up that I had for that back then. Okay. E. All right. Now this goes back probably to exam 1. This is a pretty early topic. So the tangent plane of a function at a point. So this concept is very closely tied to the idea of linear approximation, right? So the point was that to create this tangent plane, to create this linear approximation, you need to center your tangent plane at the point, and you need to make the derivatives match up. Since we're talking about the tangent plane, I'll write it in this format: z is equal to, instead of L of xy is equal to. So what you would do in the sort of general sense is you'd have f sub x of a comma b times x minus a plus f sub y of a comma b times y minus b. And so this is the formula for a tangent plane passing through the point a comma b. Right? You can see that it passes through a comma b, since if you plug that point in, this term goes to 0 because of the x minus a. This term goes to 0 because of the y minus b, and you're just left with this value. So that this is saying that at the point a comma b, the z the z position is exactly what you want it to be. It's at the correct height, this plane. And then we also make it so that the plane is has the right slopes in the x and y directions, right? We do that by making sure that if we move in the x direction, that's going to be this term. If we move in the positive x direction, then we end up moving our height of our plane up by the correct amount, which is governed by this x partial derivative evaluated at the point. And then similarly for the y direction, this is making the y direction match up. So that's why this formula makes sense. That's why you should be able to just recall the formula. Okay, now we need to actually compute this thing. So let's copy this down. So let's just y cosine of x plus sine of xy. Okay, so I'm trying to plug in at x is pi over 4, y is 2. So that's going to give me cosine of pi over 4 is root 2 over 2 plus sine of, and now this is going to be pi over 2. Okay, so I'm a little bit low on space, but let's see. Root 2, sine of pi over 2 is 1. Okay. I'm going to abbreviate. F sub x. So that'll be minus y sine of x plus y cosine of xy. Right, just taking partial derivative with respect to x. Plugging in f sub x. We get minus 2. So sine of pi over 4 is also root 2 over 2. Y is 2 cosine, and we have cosine of pi over 2, which gives me minus root 2 plus. Cosine of pi over 2 is 0. Yes, is 0. So just minus root 2. And then Fy, so we're taking the y derivative of the function f. That's going to be cosine of x plus x times cosine of xy. Plugging in the point. Let's see. Cosine of x is going to be root 2 over 2. X is pi over 4 times cosine of pi over 2. And cosine of pi over 2 is 0. Okay. Maybe I'll just do that. So we get root 2 over 2. So finally, I can plug all that data into the formula for tangent plane. So at the point, we evaluated and we got root 2 plus 1. F sub x is a minus root 2 times x minus whatever the x naught was. That's pi over 4. Plus f sub y, which is root 2 over 2 times y minus y naught. Y naught was 2. Okay. So that is the formula for a tangent plane. And I'm just going to double check that really quick. Yeah, good. All right. Part F. So we're told that f is a function of x, y, z. X, y, z are functions of u, v, and w. And you want to express the chain rule. So you don't need to draw the diagram for this, but I guess I'd do it just for you guys. So X, Y, Z, right? All of these are connected. And then it's saying that X, Y, and Z are all related to U, V, and W. So this is actually 3 times 3, 9 connections. Right? Those are all connected. But that's not the important part. The important part is you just write down the partials. So this is a multivariable chain rule, right? So all the different ways to go from F to U. So you have dF dx times dx du plus df dy times dy du plus df dz times dz du for df du. And since I can copy paste, why don't I do that? Because it's pretty much exactly the same for W. Yeah. Divergence and curl. Okay, not too bad. Divergence. All right, so you just have to remember how you compute divergence and curl, which you should be able to remember from the mnemonic, right? Divergence is the dot product nabla dot f, and curl of f is nabla cross f, where nabla is this abstract vector of partial differential operations. So divergence of f ends up being the x derivative of the first guy plus the y derivative of the second guy plus the z derivative of the third guy, which is that. The curl of f is harder to remember, so I always have to write it out like so. And we compute this determinant. Okay. So, let's see. The cofactor for I, you got a 0 here, you get a minus xy there. For j, there's a minus in front, which I guess I should put down. This one gives you a minus 2x z squared. Yes. And then the other guy gives you 0. Oh, okay. And then the k gives you a yz minus this, minus this, which is a x squared. Yeah. And so, yeah. Okay. I will still clean that up just a little. It's such a minor thing, but I don't like having the double negatives there. Okay. And so our answer would be this part as well as this part. Okay. And for H, calculate the limit if it exists. The limit if it exists. All right, so with these types of problems, right, if we were to try arguing the limit existed, it would be a really strong statement because it would mean every conceivable path that one could make from, and every conceivable path that one could make to the point 0, 0, this limit would have to be the same value. So arguing that's true is hard, right? There's a lot of different paths and infinitely many different kinds of paths. And so usually that's not going to be the case. I mean, if it is the case, there is kind of a technique, although I'm there are, I think, issues with it, so I haven't thought about that in depth. But the point is, with this problem, you should anticipate. The point is to somehow get different values, to find two different paths where this limit gives you two different values. And if that happens, then you can conclude the limit doesn't exist. Right. The point is to figure out what is, well, the key path that gives you the different value. I'm not sure how to explain how exactly to see it, but I guess the point is that you need to get some cancellation to happen in the path that you pick. So usually the right way to do it would be to think about how do you combine these things in the denominator in such a way that there's a nice cancellation that happens at the end. So you should be able to figure it out, right? This is the biggest, most significant part about this is figuring out this path. So along the path x is equal to y squared, if you use this path, then the limit becomes, so in this case, the way that I think about it is I'm actually thinking about replacing the x by y squared. And so we'll end up with a function in terms of y, and we're going to set y, we're going to make y go to 0. The numerator becomes y to the 4th. The denominator becomes, as you can see, a y to the 4th plus 3y to the 4th, so you get a 4y to the 4th, which simplifies to 1 over 4 inside the limit, which is clearly going to be 1 over 4. Right. So technically, there's two steps that I'm suppressing here. If you want to be super pedantic about how limits work, right? First, you simplify inside. You do an algebraic simplification, and then you're taking the limit of a constant, which is just that constant. All right. Next, basically, you can pick any other path. I would pick convenient paths. I would pick either x-axis or y-axis. So I'll pick x-axis. So we set y equal to 0. Then the limit reduces to, so we approach along the x-axis, so we let x go to 0. Setting y equal to 0, this function becomes that. Algebraically, this simplifies to the value 0, so you're taking the limit of 0 as x goes to 0, which is simply 0. Okay. So then we can conclude limit does not exist since different values along different paths. I guess different paths give different values. Different paths gave different values. Yeah. Sounds right to me. And, okay, extra credit. Last problem. Oof. Divergence theorem to evaluate this. Okay, so this is a double integral. Notice that this is not curl, right? So it's not a curl vector field necessarily. So Stokes' theorem doesn't seem to apply. So divergence theorem relates this with a triple integral over the divergence of the vector field, which ends up being a potential function. Right. But it requires that the triple integral is over the region enclosed. So S must somehow be the boundary of a solid region. What is S? Let's try to visualize what that is. S is a sphere of radius 3 with those two parts cut out of it. So if we try to draw this, Z is less than 0. Okay, so I had to put 3 somewhere. And Y is, okay, I had to put minus 3 somewhere. That looks right, kind of. It's a... What is going on here? So the problem is that there's this circular portion, and it's kind of doing something like that. So this is actually a fourth of a sphere, or a fourth of a sphere. So one of those planes chops it in half, the other one chops it in half again. So we have 1/4 of a sphere. Z is negative and Y is negative. So X can range from -3 to 3. And so you'll notice that it's not really drawn. Something still looks wrong about how I drew this. I don't know if it's... Does that make it look any better? Not really. Well, you can see that there are three faces to this solid, or three. I guess you could call them faces. So there's this one on the XY plane. There's this one on the XZ plane, and then there's this spherical portion. Okay. So what is helpful here in this problem is that it tells us that S is defined to be all three of them, right? If that wasn't the case, then you'd have to like do some subtraction of different things after you use divergence to set it up correctly, and then you'd have to you would still have to compute surface integrals. I'm talking about like if this problem was instead only if S was only defined to be along the spherical piece rather than including these other two semicircular parts. If S was only the spherical part, you would have to compute 2 surface integrals as well as the volume integral, and then subtract. You'd have to do volume integral minus the 2 surface integrals to equal the spherical part. Thankfully, we don't have that. We have S is all 3 parts. So, by divergence theorem, this double integral is equal to this triple integral of the divergence. Divergence we can compute pretty quickly, and we probably want to think about how to set up this triple integral. So because it's a sphere, we're going to use spherical coordinates. How do we parameterize this sphere? So it's a sphere of radius 3. Well, really it's going to be a ball. We include the interior when we're talking about the three-dimensional this three-dimensional region, this E, right, that we call this thing. So rho is going to range from 0 to 3. Theta might be easier to think about. Theta in this picture, okay, I need to kind of draw another picture off to the side. X and Y. We are given that Y is negative. So we're talking about this part of the XY plane. You could call this from pi to 2 pi, but I would prefer to think about 0 rather than 2 pi. So I'm going to call this minus pi to 0. Right, we want the orientation to be the standard orientation. namely counterclockwise. So we want to be integrating over this region in a counterclockwise fashion. Lastly, phi in this case. So that's the angle of inclination from positive z. So that's going to start off at pi over 2 and end at pi, right? Although this point over here, although this point over here, the point is that phi is always supposed to be between 0 and pi. So this point here is actually phi equals pi over 2, but theta is equal to negative pi. Or, is it negative pi? It would be over here, so not negative pi, but negative pi over 2. So the point, like, this guy is the same angle of inclination as this point over here would be. And so that is just the angle pi over 2. Okay. Let me undo that point. I don't need that point. Okay. Then we can compute this integral, I think. So I'll give myself space for the bounds. We can probably take the derivative in our head, the divergence in our head. So 2x plus 1 plus 0. 2x plus 1. Oh, I have to insert that in. Alright, I'll write that off to the side. Divergence of f is 2x plus 1. Because since we're setting this integral up for spherical, we actually need more space than that. We're gonna need to replace x. So looking at the formulas for converting x, that is rho cosine theta sine phi, and we would have a plus 1. And since this is in spherical coordinates, we have the Jacobian rho squared sine phi. Since this is a spherical box, it doesn't matter what order we do this. I'll pick the standard d rho d phi d theta. D rho d phi d theta. So theta runs from minus pi to 0. Phi runs from pi over 2 to pi. And rho goes from 0 to 3. Okay. More space for that. Right. Now, is there any simplifications I can do? I think I have to distribute and then split the integral over both terms. Then I can simplify. Can I do all those steps in my head? I think so. So for the first term, we're going to have a... maybe not. So 2 rho cubed cosine theta sine squared phi. Alright, so let's abbreviate that. Plus rho squared sine phi. And I'll just say dv because I'm abbreviating it again. All right. The point for doing that is now I can spell it out. If I keep it in standard order, d rho d phi d theta. Okay. D theta cosine theta d theta plus, and now it's d rho d phi d theta. So d rho d phi, and then d theta, which is just going to be 1. Alright, now for all those bounds. So the rho goes from 0 to 3. Okay. The phi, pi over 2 to pi. And then theta goes from minus pi to 0. Alright. So that is what this line becomes if we're trying to exploit the fact that we can rewrite triple integrals as products of three one-dimensional integrals. Do I see any cancellations here? So there is a cancellation that is nice. So this guy is 0. Right? When you integrate that, you get sine evaluated at 0 and at negative pi over 2. Sine at both of these is 0, so it's 0 minus 0. So this entire first term is 0. This second term does have stuff. So it does contribute something. I think, yeah, every single term has something there. The very last guy, that's just going to immediately give you a pi, right? The integral with respect to theta, that going from minus pi to 0, that's length. That integral has length pi, so it's pi. Integral of sine is negative cosine. Evaluate from pi over 2 to pi. So this ends up giving you, let's see, pi times, actually no, I can, 27 divided by 3 gives you 9, and then this last term, I'll pull the negative out, and then I'll think about cosine of pi. So cosine of pi is negative 1 minus 0, I think. Yes. And so this ends up giving you 9 pi as the answer. Nice. Okay, and so that's it. That's every problem on the practice exam.